The target is a Lockheed F-5A-10-LO Lightning. This specific aircraft is an unarmed photo-reconnaissance variant derived from the P-38G fighter airframe. Engineers stripped the nose compartment of all armament and ammunition bays to install sensitive camera equipment. This configuration relied entirely on altitude and speed for survival. The airframe carries United States Army Air Force's serial number 42-13084. The objective is to document the physical baseline of this reconnaissance platform, but the record is thin. Available sources still do not pin down the lost date, and no primary mishap report has been located in public archives. The wreckage rests in the Waigani Swamp within the Port Moresby airfield area of Papua New Guinea, commonly described as near the Jackson Strip boundary inside the wider drome complex. We have its verified serial number. We do not have the operational decision matrix, the pilot inputs, or the cascading mechanical failures that forced the aircraft into the mud. Before the aircraft ever reached the humid environment of the South Pacific, it accumulated a documented baseline of severe structural trauma. In June 1943, the aircraft suffered a forced landing after an engine failure and fire at Peterson Army Airfield in Colorado. The available accident listings describe the result as substantial damage. An engine fire can compromise heat-treated aircraft-grade aluminum and drive extensive inspection and replacement of damaged structure. Engineering crews carried out major stateside repairs, removing compromised skin, inspecting critical structure for heat and impact effects, and rebuilding damaged sections to return the aircraft to serviceable condition. Following that work, the airframe was deployed to the Pacific Theater. This earlier thermal and physical stress fundamentally alters our forensic baseline. Any structural assessment of the current wreckage must carefully differentiate between the repaired Colorado fire damage and the ultimate kinetic trauma incurred during its final Pacific operation. That final operational flight ended in a loss whose fine details were never pinned down in a surviving primary report. The wreckage came to rest in the Waigani Swamp area near the Port Moresby airfield complex. With the official mishap file still missing, the approach path, the failure chain, and the touchdown dynamics remain unknown. Investigators can only frame hypotheses from the geometry of the wreckage and its relationship to nearby prepared surfaces, whether a runway excursion, a rejected takeoff, or an off-field forced landing into swamp terrain. We can verify the resting location, but the exact airspeed, pitch attitude, and power settings at the decisive moment cannot be proven from documentary evidence alone. The final resting environment immediately dictated the physical preservation of the surviving airframe. The Waigani Swamp is a shallow, aquatic environment. When the aircraft settled into the soft mud plain, the lower fuselage, the landing gear doors, and the lower engine nacelles became deeply submerged in wet sediment. This specific resting geometry triggers the mechanics of oxygenated mud degradation. A waterlogged freshwater swamp severely restricts atmospheric oxygen from reaching the submerged aluminum skin. This oxygen deprivation can slow some corrosion mechanisms on deeply buried sections by limiting fresh oxygen and water circulation. However, the upper airframe components remain permanently exposed above the mudline. Fluctuating seasonal water levels subject these upper engine cowlings, canopy frames, and upper wing skins to continuous wet and dry cycles. This constant wet and dry cycling accelerates severe corrosion along exposed rivet lines, seams, and stressed structure. The engineering trade-off is absolute and unyielding. The dense mud buries and protects the lower half of the aircraft, while the relentless water cycle systematically destroys the exposed upper half. The location provides visual confirmation of identity, but it offers no formal operational closure. With documentation absent, the reconstruction has to come from the airframe itself, tail boom alignment, deformation patterns, and the condition of the forward landing gear attachment points. Those indicators must explain how a heavy twin-engine aircraft left prepared surface and entered swamp terrain without high-speed fragmentation. The Port Moresby airfield environment sits close to sea level, and Jackson Strip is commonly listed at about 124 feet above sea level. Beyond the hard edge of prepared surface, the ground can transition quickly into poorly drained swamp terrain. This geographic limit provides zero margin for an aborted takeoff or a landing overrun. When an aircraft departs the runway, it immediately strikes a shallow, waterlogged mud plain. The terrain creates a hard geometric boundary that forces a high-energy kinetic event to dissipate within a very short physical distance. The wreckage of the Lightning came to rest precisely in this transition zone, locking its physical history directly off the end of the airstrip. The exact coordinates placed the airframe entirely within the swamp boundary, completely removed from the operational flight line. The physical mechanics of a runway overrun into a marsh fundamentally dictate the structural condition of the wreckage. A heavy twin-engine aircraft carrying significant forward momentum experiences immediate and severe swamp deceleration when it plunges into soft sediment. The nose landing gear typically shears backward upon contacting the dense mud. Rapid fluid drag against the lower fuselage and the engine nacelles creates a massive, unequal deceleration force below the center of gravity. This sudden lower resistance causes a violent nose-heavy pitching moment, driving the forward fuselage downward and warping the central wing spar without initiating high-speed fragmentation. The airframe absorbs the kinetic energy through severe bending stresses across its longitudinal axis rather than shattering into a dispersed debris field. Once forward motion stops, the heavy engines and lower fuselage sink into the sediment, locking the Lightning into a static, half-buried posture. Thick mud clamps the lower structure in place, preserving the overall outline even as components fail from the initial deceleration. Above the mudline, exposed skins and framing sit in open tropical air, and water can collect in recesses where it attacks seams and rivet lines. Even so, with the lower fuselage anchored in dense sediment, the wreck's overall geometry stays unusually stable, remaining largely cohesive instead of slowly dispersing. The location itself imposes a strict operational salvage limit. Heavy recovery equipment cannot easily work in a shallow, waterlogged mud plain so close to operating surfaces. Recovering a fully assembled twin-engine aircraft from deep sediment would have required major logistics, reinforced lifting points, and stable crane ground that were not immediately available, so the hulk was left in place. Its twin tail booms, central nacelle, and wing sections stayed recognizable, turning the wreck into a long-lived fixture at the swamp margin. Half buried in shallow water and mud, and the wreck remained structurally compromised yet largely intact in overall outline for decades. Disturbing that long stable posture introduces new handling stresses and fresh oxygen to surfaces the mud had sheltered. The precise physical methods used to extract the derelict hulk are still not captured in a surviving, detailed lift plan. The salvage date is reported inconsistently, listed as November 1978 in some accounts and as July 18, 1979 in others. The lifting points, the rigging configurations, and the mechanical support systems utilized by the recovery teams remain unknown in the records available. We know the recovery was carried out under institutional direction in Port Moresby, and secured the wreckage into museum custody. It is commonly described as being dragged from the swamp margin and then moved by heavy equipment onto transport for relocation. However, the subsequent 23 years spent in this uncontrolled environment created a severe conservation trade-off. After recovery, the airframe was placed in an open-air museum yard with no climate control or overhead shelter. Set directly on the ground, already compromised structure was exposed to ultraviolet light and constant tropical rainfall, and the institution could provide security, but not chemical stabilization. The same move that freed the aircraft from mud also reintroduced abundant atmospheric oxygen to previously shielded lower components. In high humidity and daily temperature swings, condensation persisted inside wing roots and central nacelle bulkheads, so driving galvanic attack at dissimilar fasteners and pitting and exfoliation in the aluminum skin. The wreck shifted from a static, supported posture into an active decay state that steadily erased load-bearing thickness. Over the next 23 years, atmospheric exposure steadily stripped strength from ribs, cockpit flooring, engine mounts, and the attachment points that tied the twin tail booms to the wing. Rainwater pooled inside open sections, driving localized attack along rivet lines and seams, while heat and rain cycling pried joints open and pulled skins away from their formers. Repeated inspections showed a wreck transitioning from a single airframe into brittle, failing sections, secure from scrapping but sliding toward collapse. By 2001, the question was no longer how to preserve a complete Lightning, but what could still be saved before the remaining geometry failed? The engineering team faced a hard binary choice regarding the surviving aluminum structure in 2001. They could either attempt an impossible standalone restoration or strategically harvest the airframe for a higher priority project. Because the continuous open yard exposure permanently compromised the primary load-bearing structures, a safe standalone return to flight status was strictly impossible. The structural yield strength simply could not support operational flight stresses. Robert Greinert, representing the Historical Aircraft Restoration Society, initiated the decision to convert the F-5A into a dedicated donor airframe. The surviving components were officially designated for extraction and export to Sydney, Australia. Converting a derelict aircraft into a donor airframe requires disciplined procedural disassembly rather than basic mechanical salvage. The extraction team arrived at the site with a strict harvest mandate. They systematically evaluated every surviving component against the exacting engineering requirements of their target restoration project. They identified the rare early model sheet metal sections and the complex internal structural ribs that remained geometrically intact. To extract these viable pieces, the crew executed a highly controlled dismantling procedure. Basic cutting tools generate excessive heat and vibration, which easily warp aged aluminum. Instead, the engineers drilled out large numbers of individual factory rivets to separate skin panels from underlying structure with minimal added heat and vibration. This meticulous extraction method isolated structurally viable sheet metal and intact internal geometry without inflicting unnecessary secondary stress. The team specifically targeted the unique nose compartment structure, the surviving tailboom sections, and the highly complex wing root fairings. These specific areas define the exact aerodynamic profile of the reconnaissance platform. These harvested components serve two distinct mechanical purposes. Pieces retaining sufficient structural integrity were prepared for direct integration as physical splices into the recipient airframe. Components deemed too brittle for active flight loads were immediately designated as hard tooling templates. Even when a specific aluminum skin panel suffers from severe localized material failure, its overall dimensional shape remains perfectly accurate. Restoration specialists use these extracted pieces as flawless three-dimensional blueprints. They clamp fresh aircraft-grade aluminum directly over the salvaged skins to reverse engineer the complex aerodynamic curves. This physical template engineering effectively bypasses the critical need for missing original factory drawings. The total production run for this specific reconnaissance variant was extremely limited, commonly cited at about 180 F-5A aircraft, with some references listing 181 completed. This exceptionally low production number meant that replacement parts simply did not exist in any global aviation inventory. The engineering decision to harvest the Papua New Guinea wreckage provided the absolute only viable path to acquire the necessary structural geometry. The physical disassembly required securing the brittle aluminum before long-distance transport. Every harvested section needed rigid external bracing to prevent the delicate bulkheads from collapsing under shifting loads during the maritime shipment. In 2001, the carefully separated parts were packaged into heavy transport crates for the final export to Sydney. This technical operation required a strict, irreversible engineering trade-off. By prioritizing the collection of usable splices and dimensional templates, the recovery team intentionally dismantled the surviving structural cohesion of the Lightning. The systematic extraction permanently erased the distinct physical footprint of the F-5A airframe. The aircraft transitioned completely from a cohesive, recognizable historical artifact into a decentralized collection of detached industrial components. The technical execution of this disassembly plan was highly successful from an engineering standpoint. The required parts were carefully isolated, structurally secured, and successfully relocated to the restoration facility without losing their critical dimensional accuracy. The donor program fully achieved its mechanical objective by acquiring the rare physical templates. What happens when the systematic extraction of national war surplus bypasses sovereign chain of custody protocols? The official parliamentary record investigating the 2001 export contains a glaring documentary error regarding the identity of the extracted wreckage. In that record, the aircraft is listed as an F-54 Lightning, and a designation inconsistent with standard wartime type markings, and with the F-5A identity tied to the serial number. This mismatch signals a breakdown in administrative accuracy and oversight during the extraction process. Historical wreckage within national borders is treated as sovereign war surplus, and any extraction and export depends on a documented chain of custody, title transfer, customs declarations, and explicit government clearance. In this case, crates of reconnaissance components left Papua New Guinea without those approvals, prompting the Papua New Guinea Public Accounts Committee to open a formal inquiry into the National Museum and Art Gallery. The committee traced the breakdown to museum-level oversight. Officials facilitated release of the material without recorded government authorization or entry in a state ledger, and the export paperwork was later treated as lacking clear lawful authority. Once the parts were overseas, the inquiry could document the breach, but had limited practical leverage to compel physical repatriation. With custody unresolved and the hardware already outside the border, the story shifts from sovereign control to what engineering does to heritage when artifacts are dispersed into a larger project. The ultimate engineering trade-off for the exported F-5A sheet metal was the loss of a standalone identity in order to support the completion of another Lightning project, reported as the recipient serial number 4-2-12647. Once the harvested components arrived overseas, they were treated as donor material, splices, patterns, and structural references intended to help complete a coherent display airframe. A composite rebuild relies on a highly disciplined physical amalgamation. Engineers combine surviving sheet metal, main wing spars, and complex internal bulkheads from multiple different wreckage sites to yield a single, complete visual display. They must align the donor pieces with the primary recipient framework using rigid external alignment jigs to ensure absolute aerodynamic symmetry. During this procedure, the technicians cut, shape, and splice the original donor aluminum to achieve exact structural continuity with the recipient airframe. This mechanical integration creates a cohesive and structurally sound machine suitable for static museum exhibition. However, this process permanently destroys the distinct mechanical footprint and the individual operational provenance of the donor aircraft. The resulting structure is a physical hybrid, built from distinct components that experienced entirely different environmental and operational histories. The technical integration of the reconnaissance components required exacting physical modifications. The surviving tail boom sections and the unique forward fuselage bulkheads from the donor aircraft were systematically riveted into the load-bearing pathways of the recipient P-38F airframe. Mechanics had to address minor geometric variations between the different production blocks, forcing them to manipulate the donor metal to fit the new application. Every time a salvage panel was attached and riveted into the new frame, the unique physical context of the F-5A was further diluted. The original factory tolerances, the localized operational stress wear, and the specific material fatigue accumulated by the donor airframe were permanently blended into the structural reality of the recipient machine. From a strict forensic perspective, this amalgamation effectively erases the donor aircraft as an independent historical entity. The physical material survives the restoration process, but its specific structural context is completely lost. An aviation investigator examining the newly completed composite airframe cannot easily differentiate the internal ribs salvaged from the donor from the primary structure of the recipient aircraft. The original aerodynamic profile of the specific reconnaissance platform is heavily modified or entirely discarded to match the standard fighter configuration of the target build. The specific mechanical evidence that defined the F-5A airframe is permanently buried under fresh zinc chromate primer, new structural splices, and uniform exterior paint. The restoration effort achieved a clear material win. Rare early model Lightning geometry survived as splices and dimensional templates, and the remaining metal was stabilized in controlled storage. The cost was equally clear. Serial number 4-2-13084 ceased to exist as a coherent standalone artifact once its structure was dismantled and absorbed into another build. In the finished display, uniform primer, splices, and paint intentionally hide the mixed origins of the internal parts, preserving the type's silhouette while collapsing the donor's separate operational history into a composite whole. Does that kind of composite preservation save legacy or erase it by design?